Hello students, today we are going to discuss about work done in isothermal process as well as work done in adiabatic process, and also we will discuss about isochoric, isobaric and cyclic process in this class. And before going to discuss about this, I would like to discuss about the previous class. That is, we have seen that in isothermal process, what is constant in isothermal process? Temperature is constant in isothermal process. Okay, and in adiabatic process, the amount of heat energy exchanges with surroundings is equal to constant. That means change in heat energy is equal to 0 in this case. And also we discussed about isobaric process. Isobaric, we have seen already. I have told you one trick for it to remember. Bars are the units of pressure. So in this case, isopressuric. That means pressure is constant in this case. So in this process, pressure is constant. Next one is nothing but isochoric process. In isochoric process, volume remains constant in isochoric process. So these are the four processes that we have discussed in the previous classes briefly. Now I am going to give you an expression for work done in isothermal process. So we know in isothermal process, for an isothermal process, the ideal gas equation, we know the ideal gas equation is nothing but the ideal gas equation is, we know that PV is equal to nRT or mu RT. PV is equal to nRT. Here in isothermal process, as temperature is constant, we know that N is also constant because it is the number of moles of a given substance is always constant. We know that. And R is nothing but universal gas constant. R is also constant. So nRT is also constant. Multiplication of nRT is also constant. So an ideal gas equation will become PV is equal to constant for the case of isothermal process. So this is nothing but simply isothermal process. Ideal gas equation for isothermal process is nothing but simply which is Boyle's law. In Boyle's law, we know that PV is equal to constant at constant temperature. Pressure into volume is equal to constant. That means pressure is inversely proportional to volume at constant temperature. This is nothing but Boyle's law. We have known this already. We discussed already. Pressure is inversely proportional to volume at constant temperature. Okay. Now, in isothermal process, whenever a system passes through different states of the medium, different states, when consider the state is moving from P1 V1 to P2 V2. State of the gas is changing from P1 V1 initial state to final state. So here I am writing it as a work done. Work done is nothing but work done by gas in isothermal process is given by in isothermal process. We have discussed already the for any process the system has to undergo quasi-static process. When it is undergoing quasi-static process, let initially the pressure of the gas is P1 and initial volume is V1. Let it is moving from one state to another state. Quasi-static process means very slow process. Let P1 initial pressure is pressure and change in volume is V1 plus delta V. So here by keeping the pressure as constant, we are changing the volume. So it is nothing but some intermediate stage. In an intermediate state, the state of the system is changing from P1 V1 to P1 comma V1 plus delta V. So here pressure is constant, but only what is changing here? Volume is changing. For this is for intermediate state only, not strictly for total process. Okay. In this case, only temperature remains constant. I am considering only one intermediate stage in which the pressure is P and volume is changing from V to V plus delta V. So change in volume will become delta V. For that intermediate process, for that process, work done, the small amount of work done is nothing but P delta V. P delta V. And for this process is infinitely slow. So that delta W is nothing but it is a change in work done, small amount of work done. If amount of work done is still infinitely small, in that case we can express delta W with dW. So dW is equal to PdV. Now I am integrating on both sides for equation 1, integrating on both sides. If we integrate on both sides, we will get total work done. I am integrating on both sides here. So net work done, integral dW is nothing but integral PdV. Here what is changing? Volume is changing. From where to where? Initial volume to final volume V2. Let us consider this is equation number 2. We know that PV is equal to nRT. From ideal gas equation, PV is equal to nRT. Okay. From this, we can write pressure P as nRT by V. nRT by V. Substitute this equation in above. Substitute this expression in above equation. So integral dW is nothing but simply W, total work done, is equal to integration and derivation cancel, so we will get W, work done, is equal to integral, limits are changing from V1 to V2. I am writing pressure as nRT by V into dV. I am writing dV as it is. So now Na is constant, number of moles is constant, R is universal gas constant, which is also constant. For isothermal process, temperature is also constant. We can take these three as common. So now I am writing work done equal to nRT integral 1 by V into dV, where limits changing from V1 to V2. We know that integral 1 by x into dx is nothing but ln x. This is the formula, you have to remember it. Ln x, or we also can write it as log x base c. Ln x is nothing but log base c. So here 1 by v integral dv is nothing but ln v, natural logarithm of volume. So w is equal to nRT. Now I am writing it as ln v. And limits from v1 to v2. Apply the final limit first. Wherever v is there, just keep final limit nRT into ln. Final limit is v2 minus apply the initial limit wherever v is there. So I am applying the initial limit ln v. Right? Now I will get work done is equal to nRT. This is in the form of log A minus log B. We know that log A minus log B is nothing but log A by B. This is the formula which we have learnt in mathematics. So log V2 minus log V1 is nothing but log V2 by V1. This is the work done expression in case of isothermal process. In case of isothermal process. Okay. So here, dear students, see here we know PV is equal to constant. That means P1 V1 is equal to P2 V2. That is product of pressure into volume at initial stage must be equal to product of pressure into volume at final stage. We know that pressure into volume equal to constant here, as T is constant, as temperature is constant, PV is equal to constant. So I am writing this as PV equal to constant, P into V equal to constant. That means P1 product of pressure and volume at initial stage must be equal to product of pressure and volume at final stage. P1 V1 equal to P2 V2. So I am rearranging these terms like this. P1 divided by P2. P1 divided by P2 is equal to V2 by V1. Therefore, we can write work done in isothermal process as nRT log V2 by V1. This expression in terms of pressure also given as nRT ln V2 by V1 is nothing but simply P1 by P2. This is in terms of pressure. So this is the final expression for work done in isothermal process. In terms of volume is given, in terms of pressure is also given. And see here, the PV curve for constant temperature process, the PV curve for constant temperature process, that is isothermal process. In isothermal process, the PV curve is called as isotherm. So, at constant temperature, the PV relation will look like this. This is nothing but pressure, and I am taking volume on x-axis. At constant temperature, as volume increases, we know that pressure PV is equal to constant. That means P is equal to constant by volume. Constant divided by volume. So pressure is inversely proportional to volume. That means as volume increases, pressure decreases. As volume increases, pressure decreases like this. We call this as isotherm. Okay, now at constant temperature, this process is going on. As temperature is constant, we know that internal energy for an ideal gas, internal energy depends only on temperature. So as temperature is constant, internal energy is also constant. So here internal energy is equal to constant. That means change in internal energy is equal to 0 in this case. So now first law of thermodynamics. From first law of thermodynamics, we know delta Q is equal to delta U plus delta W. So in this case, in constant temperature process, that is in isothermal process, as temperature is constant, for an ideal gas, internal energy is nothing but it is only the sum of kinetic energy of all the molecules. That is, kinetic energy of all the molecules purely depends only on temperature. So internal energy is a function of temperature. As temperature is constant, internal energy is also constant in this process. And change in internal energy is equal to 0. So I am substituting 0 in this place. Now, amount of heat energy given to the system that will be utilized to do work done only in isothermal process. So we can conclude that in isothermal process, amount of heat energy given to the system at constant temperature will be utilized to do work done. That work done is given by simply an equation of nRT log V2 by V1, which is also equal to, in terms of pressure, nRT log P1 by P2. Okay, so here work done is equal to nRT log V2 by V1. In thermal expansion, in expansion process, when the expansion occurs, work is being done by the gas on the surroundings. That means work done by the gas. In expansion, V2 is greater than V1. Therefore, log V2 divided by V1 is positive. That means work done is positive. In expansion, V2 is greater than V1. So ln V2 by V1 is positive. So work done is positive. That means work done by the gas. Work is being done by the gas. By gas on surroundings. Work done by the gas on surroundings. Now, in compression case, the final volume is less than initial volume. In compression, final volume is less than initial volume. So, ln V2 by V1. So, numerator is less than denominator. So, V2 is less than V1. In that case, ln V2 by V1 will come out as negative. So, work done is also negative. If work done is negative, that means compression is occurring. When will the compression takes place? Consider this is a piston. When there is a compression takes place only when work is being done by the surroundings on the system. Whenever work is being done by the surroundings on the system, then only the gas will be compressed from initial volume V1 to final volume V2. So in this case, work done is negative. That means work is being done by surroundings. On what? Work done on the system by the surroundings. Work done on the system is negative. We have discussed already. Work done by the system is always positive. So this is the conclusion of work done by isothermal process. Now I am going to explain work done by in adiabatic process. Work done in adiabatic process. So we know in adiabatic process we know in adiabatic process the amount of heat energy exchanges between system and surroundings is always constant. That means heat energy, there is no exchange of heat energy between system and surroundings. So delta Q is equal to 0. From first law of thermodynamics, we know the first law of thermodynamics is as delta Q is equal to delta U plus delta W. So if delta Q is equal to 0, so I am keeping delta Q equal to 0. So delta U is equal to delta W now. So now delta U is equal to minus delta W in this case. So here I am taking, there are two conditions. I am taking case 1, this as case 1. When change in internal energy is positive, work done is negative. This means I am going to explain in a simple manner like this. I am taking a system like this, and this system is made up of adiabatic walls, because here we are going to discuss about adiabatic process. So adiabatic walls means insulating walls which do not allow the flow of heat energy from system to surroundings or surroundings to system. That means there is no exchange of heat energy between system and surroundings. So here in this case, so see here, when is work done by the surroundings on the system? Work done on the system is there. So this is nothing but work done. Work is being done on whom? Work done on the system. By whom? It is being done by surroundings. Work done on the system is nothing but negative. When work done is negative, that means the system is going to be compressed like this. The system is going to compress it like this. In compression, the volume is less, so the gas molecules will be occupying lesser volume. So there exists a large number of collisions in between the gas molecules. So as collision rate increases, temperature increases. If temperature increases, here temperature increases when volume is decreasing, because work is being done by surroundings on the system. Work done on the system by the surroundings is taking place. So this system will undergo compression. In compression, collision rate increases. If collision rate increases, temperature increases. If temperature increases, internal energy increases. If internal energy increases, that means change in internal energy is positive. So we arrived at final conclusion. If change in internal energy is positive, that means work done on the system by the surroundings. I explained this clearly with the diagram. Okay, now case 2. I am keeping this negative sign here. So here again I am coming from delta U plus delta W is equal to 0 from this equation. Delta U plus delta W equal to 0. Now, so delta W is equal to minus delta U. I can write like this also. So, here positive work done means what? Work done by the system. Work done by the system is equal to negative of change in internal energy. That means decrease in internal energy. Decrease in internal energy. Okay, I will explain this with the diagram. So I am taking a vessel again. So in this vessel is made up of adiabatic walls, that means insulating walls, because we are discussing about adiabatic process in which there is no exchange of heat energy between system and surroundings. Now let us consider this is nothing but piston, movable piston. Sorry, this is nothing but movable piston. Okay, there are large number of gas molecules inside the vessel like this. When large number of gas molecules inside the vessel like this, when work is done by the system. So now when work done by the system on the surroundings is there, work done by the system. So work done by the system, this is nothing but system here. So system is pushing the piston upside. So here piston, system is pushing the piston outside because work is done by the system here. So because of this, the volume will be increases. Volume will be increased. So volume increases. If volume increases, that is, these molecules will be spread out at larger distances. That is, the interatomic distance between the intermolecular distance between the molecules will be increased. If the distance between the molecules increases, collision rate decreases. If collision rate decreases, temperature decreases. If temperature decreases, that means internal energy also decreases, because we know in ideal gas, internal energy is only the function of temperature. I am repeating again. Ideal gas is nothing but in which there are no intermolecular forces. That means if there are no intermolecular forces, there is no potential energy term in the internal energy. So internal energy is purely because of sum of kinetic energy of all the molecules, and kinetic energy purely depends on temperature. So as temperature decreases, internal energy decreases. That means final internal energy is less than initial internal energy. That means change in internal energy is negative in this case. So whenever work is being done by the system on surroundings, the internal energy decreases. So I have given the physical significance of this relation using diagram. Now I am going to obtain an expression for. So here I am not going to give you the proof for the relation between pressure and volume in the case of adiabatic process. So in adiabatic process, the relation between pressure and volume is given by, I am not going to in detail for the expression between pressure and volume, here the relation between pressure and volume is given by PV power gamma is equal to constant. PV power gamma is equal to constant. That means P1 V1 power gamma is equal to P2 V2 power gamma. So here gamma is nothing but a ratio of specific heat capacities, that is Cp divided by Cv. Gamma is equal to Cp by Cv. So it is the ratio of specific heat capacity Cp by Cv. Gamma is always greater than 1 because we know Cp is always greater than Cv. Okay. We will discuss what is the value of gamma for monoatomic gases, for diatomic gases as well as for triatomic gases in the coming chapter. So now just remember that gamma is nothing but ratio of specific capacity Cp by Cv, and the relation between pressure and volume in case of adiabatic process. In adiabatic process, PV power gamma is equal to constant. So here we know small amount of work done in adiabatic process is given by integral PdV. We have discussed already about this, and volume is changing from V1 to V2. So here I am writing PV power gamma is equal to constant. So from this I am rearranging the terms like this. Pressure P is equal to constant divided by V power gamma. So I am writing constant by V power gamma in the place of P. So integral work done, total work done equal to integral dW is equal to integral PdV. So W is equal to integral, I am replacing P with constant divided by V power gamma into dV, and limits are changing from V1 to V2. And now I am taking constant as common. Integral 1 by V power gamma is there. I am rewriting it as V power minus gamma. When this denominator comes to numerator, it will become V power minus gamma into dV, and the limits are from V1 to V2. We know that integral x to the power of n dx is nothing but x to the power of n plus 1 by n plus 1. So from this formula, we can write like this as work done is equal to some constant into V power minus gamma plus 1 by minus gamma plus 1, and limits are from V1 to V2. So here work done is equal to constant. I am writing this is constant. 1 minus gamma is constant. Minus gamma plus 1 is nothing but simply I can write it as 1 minus gamma. And what is remaining thing here? V power minus gamma plus 1, and limits from V1 to V2. So this can be written as work done is equal to constant by 1 minus gamma, and I am bringing this numerator to denominator. It will become 1 by V power minus gamma plus 1 will become gamma minus 1 plus gamma minus 1 whenever it comes to denominator. We know x to the power of n. When it comes to denominator, it will become x to the power of minus n. I just write like that. So limits from V1 to V2. Now just apply final limit wherever V is there, just to keep V2. So work done is equal to some constant divided by 1 minus gamma into 1 by V2 power gamma minus 1 minus, apply lower limit now, V1 to the power of gamma minus 1. It is not R, it is gamma, like this. So okay, so now I am writing this constant can be written as constant can be replaced with PV power gamma equal to constant. That means P1 V1 power gamma equal to P2 V2 power gamma equal to constant. So I can replace constant accordingly. Constant can be written as P1 V1 power gamma or P2 V2 power gamma. So here V2 term is there. So that I am multiplying the constant 1 by 1 minus gamma into constant divided by V2 power gamma into V2 power minus 1. v to power gamma minus 1 can be written as v to power gamma into v to power minus 1 minus this constant divided by v1 power gamma into v1 power minus 1. Okay, now I can replace constant with p1 v1 power gamma or p2 v2 power gamma accordingly. So here constant, here v2 term is there, so I am writing constant as p2 v2 power gamma divided by v2 power gamma into v2 power minus 1 minus this constant is replacing with p1 v1 power gamma divided by v1 power gamma into v1 power minus 1. So here this v2 power gamma and v2 power gamma get cancels out, and v1 power gamma and v1 power gamma get cancels out. So now I am writing the final conclusion as work done equal to 1 by 1 minus gamma into p2. When this v2 power minus 1 comes to numerator, it will become just v2, p2 v2 minus p1 is there, and whenever v1 power minus gamma minus 1 comes to numerator, it will become v1 power plus 1. That means plus 1, p2 v2 minus p1 v1. So work done in adiabatic process is given by 1 by 1 minus gamma into p2 v2 minus p1 v1, or in terms of temperature we know PV is equal to, we know PV is equal to nRT. N is nothing but number of moles, R is universal gas constant, and T is temperature. So P1 V1 can be written as nRT1, and P2 V2 can be written as nRT2. So here I am writing work done as 1 by 1 minus gamma into P2 V2 minus P1 V1, or 1 by 1 minus gamma into P2 V2 can be written as nRT2 minus P1 V1 can be written as nRT1. So work done in adiabatic process is given by 1 by 1 minus gamma into P2 V2 minus P1 V1, or which is also can be written as nR is common in this both, nR by 1 minus gamma into T2 minus T1. This is final expression for work done in the case of adiabatic process. Okay, so now students, I am going to tell you an important thing here. We know in isothermal process, PV is equal to constant, and in adiabatic process, PV power gamma is equal to constant. PV power gamma equal to constant. That means slope of adiabatic curve is greater than slope of isothermal curve. We call isothermal curve as isotherm. So just remember this. There is block. Slope of adiabatic curve is greater than slope of isothermal curve, because PV power gamma equal to constant in the case of adiabatic process and PV equal to constant in the case of isothermal process. we can prove this by, this is beyond the scope of the syllabus. So simply just remember this. So I am writing pressure versus volume curves again. So see here, let us consider this is PV curve, this is isotherm, and this is nothing but adiabatic curve. We have discussed slope of adiabatic curve. This is adiabatic curve. Slope of adiabatic curve is more here as compared to slope of isothermal curve. This is the PV curve for both isothermal process and adiabatic process. Now I am going to discuss about isochoric process. Now isochoric process. In isochoric process, we know volume is equal to constant and the change in volume is equal to 0. So work done is given by P delta V, as change in volume is equal to 0, work done equal to 0 in isochoric process. If work done equal to 0, from first law of thermodynamics, we know delta Q equal to delta U plus delta W. Amount of heat energy given to the system, partly utilized to do work done and remaining part is to do increase the internal energy. We know this first law of thermodynamics. So as work done is equal to 0 in this case, whatever the heat energy supplied to the system, that will be utilized to increase its internal energy only in the case of isochoric process. Okay, so this is all about isochoric process. Now I am going to discuss about isobaric process. Isobaric process means in which pressure remains constant. Isobaric process. In isobaric process, pressure is constant and we know work done in isobaric process is given by, work done equal to P delta V, that is nothing but P into delta V is nothing but V2 minus V1. Okay, so in isobaric process, since temperature changes, so internal energy also changes. Whatever the heat absorbed goes, okay, here the amount of, from first law of thermodynamics, it is given as delta Q equal to delta U plus delta W, and amount of heat energy given to the system partly utilized to increase the internal energy and remaining part is to do work done by the system on the surroundings. So that's why amount of heat energy supplied to system at constant pressure is called as Cp, which is greater than Cv. We have discussed this already in the previous class. Now I am going to discuss about the final process, that is a cyclic process. Cyclic process is nothing but in which the system comes back to the same position after going through different stages of the system. In cyclic process, the thermodynamic system will come back to same position as same state as initial state. So in this case, initial state and final states are same. So we know that internal energy is a state function. As initial state and final states are same, so internal energy is equal to constant. That means there is no change in internal energy. That is, change in internal energy is equal to 0 in the case of cyclic process. So now from first law of thermodynamics, we know that the amount of heat energy supplied to the system partly to increase the internal energy and remaining part is to utilized by work done by the system on the surroundings. So here amount of heat energy supplied in the cyclic process will be goes in the form of work done by the system on the surroundings, because in the case of cyclic process, initial and final states are same. Initial state and final states are same. So as internal energy is a state function, so internal energy constant, that means change in internal energy equal to 0. So from first law of thermodynamics, delta Q equal delta U plus delta W. I am keeping 0 in the place of delta U, so simply delta U becomes delta W. So whatever the amount of heat energy supplied will be utilized to work done by the system on the surroundings. So this is the end of the class, students. Have a nice day. Thank you. Bye bye. End of this class. Bye bye.